Hi everyone, this is your struggling CS student, and today let's solve another LeetCode problem of the day. Let's take a look at today's problem. 1526, minimum number of increments on subarrays to form a target array. Okay, you're given an integer array target. You have an integer array initial of the same size as target with all elements initial at 0. In one operation, you can choose any subarray from the initial array and increment each value by 1. You are to return the minimum number of operations to form a target array from initial. The test cases are generated such that the answer always fits into a 32-bit integer and is a 1800 rated question. Okay, so let's take a look at some examples. We need at least 3 operations. We increase like so, increase like so, increase like so, and then the target array is formed. Do this, do this, do this, and you achieve like this, okay? 7 operations. So increment it like this, increment here by 1, 2, then increment here by 2, increment here, okay, then increment this, there you go. Oh, okay. Target length is 10 to the power 5, and target of I is up to 10 to the power 5. Huh, interesting. The acceptance rate is quite high actually. How will we do this? The minimum number of increments on subarrays to form target array. I'm not sure, but when I think of minimum number of operations, I always think like, okay, is there like a greedy property that we can abuse? Is there a possibility of dynamic programming? But then I see subarrays and I'm thinking like sliding window, okay? Then, so I mean, one possible solution is you can probably do binary search on actually that's not true. In one operation, you can choose any subarray from initial and increment. I guess technically you can. So you will do like a binary search on the solution space. You would say the minimum number of operations would be like 0. If let's say the initial array is equals to the target array. So for example, if your target array is all zeros, and then you can do a binary search on like the sum of the elements in target that will represent the maximum number of operations that you would need, because in that case, the simple case would be you choose every subarray of length 1 and just increment it by that number of times, right? So afterwards, what you can do is the check function is the hard part. Like how would we determine the whether like a particular guess is correct? So what I mean to say is, let's say we take this example, right? X Kelly. we would say okay, the minimum number of operations is possibly It's possibly 0 to sum of all the elements here. That will be 15, right? Technically, you could just increment it 1 at a time, right? Like so, etc., etc. And you will see that actually even 14 number of operations would probably suffice. Yeah, there is like some sort of distribution of operations such that, you know, this is definitely possible. This is definitely possible. There's no way we can achieve the target array from our initial array of 0 if we only have 0 operations, or 1 operation, so forth and so forth, until a breaking point of The answer is 7, right? So any operations that is greater than 7 onwards is it will be valid. But the thing is, how can we, like for example, given a number x, number of operations, how do we check if we can satisfy the particular array? That's the tricky part. Hmm. If we can do that, then the answer, I mean, the problem is solved. Subarray window, sliding window. To be honest, I'm not really sure. Sliding window, how will we do it? 3. That means we need minimum three three lines here, intersections if you will. Maybe like so. Let's see. Yeah, it actually spans across the whole thing. Spans across the whole thing. Is there a particular insight that we can derive here? Don't really think it's sliding window. Because like there's no particular attribute of a window that we can abuse or take advantage of. So I'm not really sure either. Minimum number of increments. Maybe we can say like, oh, starting from this position, the first position, we actually need like 3 lines. 1, 2, 3. Okay, then we say this number is smaller than the previous number, so only 1 line can cross here, right? Because we want to minimize the number of operations. And in that case, for any particular line, we always want to extend it uh, as uh, as much as we can. But because of this element, it's kind of like blocking these 2 lines, right? Suppose this was like 10 instead. If this was 10, this means that all 3 lines can go past here, right? But then we come here and we know that, oh, actually we need like 7 more lines, whatever that is. Then once we come to here, only 5 lines would survive. Then only 4 lines would survive, and 2 lines would survive, etc., etc. Okay, let's go back to this example, right? So out of the 3 lines, only 1 line would survive, and then from here, we know that we need 4 other lines at least. So it would be like this: 2, 3, 4. Okay, 1, and in this case, this line would survive, this line would survive, this line would survive, this line would survive. 1, 2, 3, 4, but this wouldn't. This wouldn't. So then we say, okay, this line would survive, this line would survive, and then this wouldn't. Then we just count the number of lines. So what are the number of lines? We have 1, 2, 3, 4, 5, 6, 7. Yeah, we have the algorithm in a sense, in the conceptual sense, but how do we actually like implement it, right? So we have to keep track of the number of segments. Okay. So when do we need a new segment, right? So we can say like, okay, the current number of segments is 3, or the first element, right? Do we always have one element? Yes, we do. Then we say, okay, if the number is smaller, then our segments, the ones that survive, would be, I guess we need to keep track of like the total number of segments and the current number of segments. So current number of segments at I equals to 1 is 3. I guess total is also 3. I'm not sure. I'm not sure. So at this point, we take like C is equals to the min of C, and like num sub I, right? I'm just gonna do like this, num sub I. So at this stage, at I equals to 2, sorry, at I equals to 1, we say that we update our current. So our current would be like 1. In this case, then we need 5. We need 5. But we know like these two is like dead. But how do we know those two are dead? We need like 4 other lines here. So if the array is like 3, 1, 5, what would the answer be? Be 1, 2, 3, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. It's actually the same as 3, 1, 5, 4, 2. Okay, okay. I guess we can have like, I don't know, a function that can give us the like the next ID of, then we keep track of the IDs. No, but that's not good, right? Because I don't know, it might be possible to construct like an n squared case, but target of I is up to 10 to the power of 5. Interesting. We need 4 more lines. Okay, okay. Let's take a step back. So here we would say like we need a +3 -2, then we need like a +4, like 1, 2, 3, 4. Here is 3, 4, -1, -2. So +3, -2, +4, -1, 1, 2, 3, 4, -2. What is this? This is 1 + 4, that's 5. Okay, let's do it one step at a time. 3 - 2, that's 1. +4, that's 5. -1 -2, you get 2. What does this tell me? What is these 2 lines? I don't know. Let's take a look at another example and see if we can derive any insights. 1, 2, 3, 2, 1. So this is +1, +1, +1, -1, -1, right? So that would be +1. Answer here is 3. It doesn't tell me anything at all. Just tells me the need 1 line here, need 2 lines here, need 3 lines here, 2 lines here, 1 line here. I'm not seeing any patterns yet. How about this one? 3, 1, 1, 2. Actually, this is quite a good example because you have like 3 and then you have less than 3 and then more than 1, right? So basically what I'm trying to say is the next element is smaller than this number, and for a particular element this is also bigger. So we have like two cases already. I guess the only other case that we're missing would be what happens if they're equal, right? Let's say we have like uh 5 in this case. It actually doesn't really matter, but how about we put it at the end as well? I think for case 5 is still 7. Yeah, this one I'm not so sure. 10. We need 10. Okay. Uh, let's see. 5. Here we would actually do 1, 2, 1, 2, 3. All right, so it's 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is plus 3. So what does that mean? This is 5 minus 3. 2, 2 plus this is 5. This is 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. uh, One operation, you can choose any subarray from the initial and increment each value by 1 to the minimum number of operations. Oh, wait, I think I noticed something. Plus 3, plus 4, and plus 3. This gives you 10. What about here? I think I might have gotten it, but let me just double confirm. Yeah, yeah, okay. Wow, I think I actually got it. Basically, what happens is you keep track of the current number of lines that you need, right? So at this part, your current number is like 0, right? Then you say plus 3 because in order to successfully um, decrement or increase the initial target of I and no, no, current of initial of I to target of I, you need at least 3 lines here. So okay, then you say we draw the 3 lines there, right? Let me just clean this up. Yeah, I think I actually got it. Cool, cool, cool. So basically, the idea is you look at the positives and you just take that as your answer. I'm gonna explain why that works, and then we will implement it. So let's walk through an example, like so, right? Okay. So you only need to keep track of the current number of lines and your total, I guess. So your total is 0 and your current is 0, right? Mm, let's put it here. So what happens is, at this point you have 0 number of lines. So you at least need 3 lines here, or 3 segments or 3 subarrays that covers this particular element. Okay, then you say you update your total is 3, update your current 3 segments. Then you say, okay, at this point, um, these 2 segments will not survive. So this one and this one, they wouldn't survive, if you will. They can't make it past the 1. So in this case, you would say you take the difference between them. You take the difference between them. So it's like 3 minus 1. No, let's do the opposite. You take 1 minus 3, you get -2, I guess. Okay, -2, what this means is that uh, this is the number of lines that you would lose. So, okay, you say 3 minus 2, you get 1, right? But you actually don't update the total. You don't update the total because, how should I say it? Uh, the lines that were previously drawn, they are already drawn. So you have to make the choice no matter what. You have to make the choice no matter what. So okay, so you know that at least one line would survive past this. So when you come to a number that is bigger, right? Take five, which is the next element, minus the the number of segments that you have, number of current segments that you have, which is 1. You get positive 4. What this means that is that at this stage, you minimally you have to draw 4 more lines. There's no way around it, right? There's no way around it. So in this case, you will draw 4 more lines. You say, okay, I draw 4 more lines here, 3, 4. Draw 4 more lines, update your total, 3 plus 4, you get 7. Your current number of lines is actually 1 plus 4, which is 5. So let me clean this up. So this is 7 now. This is 1 plus 4, which is 5, right? This is 7. We are at this stage of your current number of segments is 5. Then at this one is just my temporary calculation, so I'll just remove it. Okay, so now you know that you take 4 minus 5, right? You get -1. You update your current number of lines, -1, but there's no need to update your total. So update your total because you're not adding new lines. You're just removing one of the lines that you have already drawn or you're using in that case. So okay, so you say 4 lines survives. Let me update this. Your 5 minus 1, which is 4. And I say, okay, 4 here, 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 here. Okay. So now we update our traversal pointer. It's now here. Then you say that, okay, what do we say? We take the next element, which is 2. 2 minus 4 equals -2. Okay, then you update it again. You update your current. Now your current is 2, but you're not adding any new lines, which is fine. So now it becomes like this. So what happens if, let's say, we add another element, right? Add another element, and oh, by the way, when the traversal reaches the last element, we're done, right? We're done. But let's add another element. In this case, our previous example was 5, right? So we say, okay, we take the next element. We take the next element, 5 minus 2, you get 3. That means you need 3 more lines in this case. 3 more lines. Okay, so you update your current segment, plus 3, update your total, plus 10, right? So you have 2 lines here. Then you need to draw 3 more lines, 1, 2, 3. So I guess it's kind of like a greedy algorithm. If I had to guess, I'm not, I don't know what you will categorize this as, but from what you can see from the algorithm for this run through would be actually very optimal. You know, your time complexity is O(n), your space complexity is O(1) because we're just keeping track of a few variables and we're iterating through the input list just once. So let us implement the algorithm and see how it works and see if it works. Okay, so, and by the way, I think I just got lucky. You know, maybe my intuition somehow noticed some sort of pattern here and I just happened to figure out the answer. It's about, you know, breaking down the problem and identifying some sort of patterns from the examples and thinking about what are the cases you need to consider. For example, like a particular element, like 3, I know that I need to 3 lines here, but what happens if my next element is smaller? What happens if my next element is bigger? That's how I was thinking about the problem. So maybe that can give you some, I don't know, insights to help with your own LeetCode journey. But right, let's start implementing the algorithm. So our current number of subarrays or segments, as I call it, is 0, and the total, right? The total is equal to 0 as well. We'll return total. In this case, I think it's more akin to a greedy algorithm. You only add subarrays when you need it, right? We're not like, you know, using some sort of dynamic programming or binary search on solution spaces to guess the answer. etc., etc. Okay, so we say n is equals to the length of target for I in range of n minus 1. Next is equals to target of I plus 1. Then you say current plus equals current always plus equals next minus current okay, always plus target of I. Yeah, okay, let's do it like that. Maybe we don't need a next variable. Maybe this is succinct enough. Okay, so current will keep track of the number of segments, but then for this particular calculation, right, let's call this diff. Right, difference is equals to this plus equals diff. But as for our total, we always add the difference, the max of 0 and difference. So we never add a negative difference to our total. We only add difference if the difference is positive. Let's give it a spin. And there you go. All my test cases are wrong. Wait, why? Take the next element, current. Okay, I see now. So our current is always target of I, target of 0, I mean. And this will work. Still wrong. Oh shit, it's very wrong actually. Oh, that's because I need to start it from the next element. Okay, that's not good, or that's embarrassing at least. Put in current, total. Let's see what's wrong. This is not n minus 1, is it? Oh, it's n minus 1, okay. Let's see this example. Current is 7. Oh, why is it 7? I mean, what is the current, what's the current 7? This? Four. Oh, wait. Is a target of I minus 1 minus current, I think. Let's see. Current is 5. Oh no, the difference is 2. So current, target of I minus 1. Oh, it's current minus this. Target of I. Let's see. Current, the difference is 2. Wait, what did I do just now? Oh shit, it's target of I minus current, I think. So let's see. So current now 1 at index 1. That's correct. It's correct. Total. Oh, total also equals to current. Oh shit. That's not good. Did I make a mistake somewhere? Even this is wrong. No, we need to go to the last element, right? Okay. Okay, it was a little bit sloppy. I had to be honest there, but I yeah, the algorithm works. The working is a little bit messy, but the time complexity is O n and the space complexity is O1. Let's try on some random inputs and see if it works. uh, 3, 3, 3, 3. I think that's one of the test cases I'll be interested to see. Let's say 3, 1, 10, 10, 10, 5, 7, 10, 9, 1, 2, 3. Okay, it should work. Okay, I'm ready to submit it and accepted. Nice. 6 days. Solve a hard problem on my own. Actually, 1800 is around the easier range for a hard problem, right? You can even say this is like a harder medium. So let's take a look at the editorial. Readers who have seen various reference solutions to this problem may feel a complex mix of emotions, labeled as hard, yet it can be solved in only 5 lines of code. Calculate the difference between adjacent elements and keep only the positive parts and sum them up as the answer. Yep. How can we prove that this approach is correct? Difference array. Oh, interesting. I never thought of the difference array. However, there is also rigorous proof which derives an explicit operational plan using the concept of difference array. The following explanation introduces this method from first principles. Okay, okay. Okay. Okay, this guy. Holy shit! Why would you think it's segmented tree, dynamic programming, greedy, monotonic stack? Interesting. Yeah, this article looks like it might be very good, but it's quite lengthy. I'll take a look later. I'll take a look at it later. Let me just give it a brief quick read. Yeah, usually if you want to prove some sort of a greedy algorithm, you would assume the opposite by proof of contradiction, right? And you will assume the opposite, derive a contradiction, and say that, oh, therefore your greedy algorithm works, because by not doing the greedy algorithm, if we assume the opposite, we will derive a logical contradiction. But anyway, this is my code. I'm quite happy I managed to solve this one. This is time complexity is ON, space complexity is O1. That's all for me today for 1526. Thank you for watching and have a great one ahead.